Good morning. Welcome to the Invisible Talk. Okay, I'll find something to point out. See if it works. Yeah, it works. Okay, well, the pictures up here are basically representative of our very long-standing collaboration with groups across Europe, specifically the Institute of Physics in Prague. There's us there, there's Cambridge, you may have heard of them, and also, I think there's a university here, you may also have heard of. You've already heard from people like Jörg Gunderlich from Prague, from Cambridge and Prague, for that matter, talking about the results of copper manganese arsenide. You've also heard from Pete Wadley. How are you, by the way, Pete? Yeah, Pete's not feeling very well this morning, but he struggled in, which I appreciate very much. Okay, so this is the basic, if you like, collaborative group, actually expanded in recent years. And these are the people involved. It's actually a very small subset of the people that really have been involved in copper manganese arsenide, but it's a subset that it was involved at the sort of genesis of copper manganese arsenide when we first came to grow it. And unlike all the other talks, I mean, Jörg and Pete and Thomas and pretty much everybody else has given you all the brand new results on copper manganese arsenide, so there's no point in me repeating all of that. So I thought I'd give you the genesis, the way we came to this material and how we make the material and how we grew the material. Specifically, I'd like to point out my very good friend and long-term collaborator at Novak, and of course my colleague Pete, and Thomas Youngworth and Brian, who are also here as well. Okay, so I'll just talk about early ideas and then some bulk synthesis that we did right at the beginning, then copper manganese arsenide thin films, finally conclusions. Okay, a bit of history. Well, we spent lots of years, since about the year 2000 actually, growing gallium manganese arsenide, which was very... Sorry? Yeah. Okay. Oh, God. Don't you just hate these things? Okay. Yeah. Sorry about that, guys. We started many years ago growing copper manganese arsenide, and it was a wonderful prototype material to look at magnetic phenomena. The trouble with gallium manganese arsenide was that the manganese is substitutional on the gallium side, but it's a dopant. And the trouble is, if you try to put lots and lots of manganese into gallium manganese arsenide, the doping is effectively frustrated, and you have solubility problems because it's a dopant, and also it ultimately leads to compensating defects as well. So you have you're always fighting this thermodynamics. So we wanted to look for, when we started realizing the limitations of the material, we wanted to look for an analog where this wouldn't be the case. And we came up with this material, lithium zinc manganese arsenide, which in this case is a 125 semiconductor, and the manganese of course then goes substitutionally, so it's not doping anymore, so you don't get this solubility problem. So we thought, great, this is a great idea. It even fits nicely on gallium arsenide. And looking at the band structure modeling, which was done by my colleagues in Prague, you can see that it's almost identical to the band structure of gallium arsenide, same band gap. It's amazing. So this looked like a really, really promising material. Now, lithium's not very nice in MBE machines, and I didn't really want to put lithium in, or zinc for that matter, into my production machine. But fortunately, Vit had essentially a redundant machine that he was prepared to sacrifice. So essentially we sent him some bits and he started growing zinc lithium manganese arsenide. Unfortunately, now, I don't want to worry you theorists, okay? But it's not always possible to take atoms and just put them in appropriate lattice size, okay? Nature doesn't always want to play that game, and unfortunately, definitely didn't want to play that game with lithium zinc manganese arsenide. So fighting with both lithium and zinc was really difficult. In the end, it turned out actually that lithium manganese arsenide wanted to grow. It also turned out it was very interesting. It's an antiferromagnet, and of course there was interest by that time, lots of interest in antiferromagnets, so we thought, hey, we've got an antiferromagnet. Unfortunately, it was also chemically unstable. So I was getting a bit bored in Nottingham, and I wanted to do something, and so we started looking around for alternatives, and we started thinking about the 1B group, the copper, silver, gold. Okay, and of course the cheapest is copper, so I've not got much money, so we put copper in the machine, and we thought, okay, while we're getting the machine ready to grow copper manganese arsenide, we'll obviously do some preliminary work, and we did some bulk growth, so we did some bulk synthesis. Okay, so high temperature synthesized copper manganese 5s in general, antimonide, arsenide, and phosphide were all done. And the magnetic data were extremely promising. You can see here we've got the specific, the scale isn't very good, we've got specific heat, resistivity, and susceptibility. So this looked very nice, especially copper manganese arsenide with a nice high nail temperature. The phosphide looked like it might have a true gap, but the arsenide and certainly the antimonide were likely to be semi-metals. Okay? So, phosphide was probably a really good idea, but the trouble with the phosphide was we had a lot of competing reactive phases, so actually we thought we'd start with the arsenide, okay, which was kind of good luck, really, because it worked. So, there we go. So we've got a nice promising thing, and this is actually a redundant statement at the bottom, which I put in for when I'm talking to growers, because when I'm talking to growers about antiferromagnetics, usually, but this audience probably doesn't feel that way. Okay, so antimagnetic... Pardon? Okay, so bulk structure determination, and it's a relatively easy thing to find out if you've grown a bulk structure what it is. So we just went through the normal sort of steps that you would do. You do some X-ray, you find a couple of peaks, and you can find the parameters, the space group, and the intensities give you some idea of the atomic positions. And for bulk copper manganese arsenide, it turned out it was orthorhombic. Okay, A not equal to B, not equal to C, not equal to very hopeful for growing epitaxially. Okay, because we were quite worried about this, as you might imagine. So very, very difficult from the point of view of substrate selection. Well, anyway, I got the machine ready by this time, and clearly the choice of substrate is challenging. We'd like to find something, semiconductor or otherwise, but preferably a semiconductor, with lattice dimensions in the plane matching what we have, but it was very, very difficult to find such a thing. There's no easy candidates. We spent loads of time playing with crystal model software and tables of structures and so on and so forth, and we realized that it was time to wheel out the universal substrate. Now, you guys are probably thinking, hang on, how come the growers didn't tell us about this universal substrate? Well, they know, the growers know, that the universal substrate is, well, what is it? It's the one you've got most of in the cupboard. Well, I had a look in my cupboard, and my cupboard's full of gallium arsenide, so that's what we decided to grow on, basically. That's the best way. So, in our case, gallium arsenide, so that's what we used, and it also allowed us to use our band edge thermometry, which gives us very accurate readout of the temperature, so it was really quite a good idea to use this. But it's not the right crystal structure if you want to grow the orthorhombic. There's no question about that. Okay, so we've got time to have a go at MBE. And I think Vitt will remember this period very well. So we've got an orthorhombic structure. We have apparently no supertable substrate. Substrate temperature, let me see, 300, that'll do. Uncertainty about stoichiometry. We know nothing. Okay, so hands up, anyone who thinks this might be a complete mess. And we did. We thought it was going to be a complete disaster. Wow. Absolutely not. So this is the read. These are the very first growths. These are the very, very first growths. So the guesses were really good. Growth at 300. And what this, for those who aren't familiar with looking at read pictures, what this is basically showing us is that we have, because they're nice and streaky, we have nice step flow two-dimensional growth. Okay, that's what we've got. Nice flowing steps, not big lumpy things. Okay. We've got fourfold symmetry, so not orthorhombic. Interesting. We also had a look at the different fluxes. We've got a flux of 1-to-1 with the copper and manganese there, 0.9, 0.8, and 1.4, and we can see how incredibly tolerant this material is. It really wants to grow. This stuff really wants to grow. So basically, in summary, it's got fourfold symmetry. We also grew it on 110, and it had twofold symmetry, which kind of made sense. It had done something different. We tried various other different things like manganese arsenide, pseudo-substrates, sapphire, just to see what we thought we had, because we really didn't know what we had. We knew it wasn't the orthorhombic, but we didn't know what else it was. Okay, and so we tried various different things. Nothing really told us exactly what we had, but there were hints. We looked at the wafers you've just seen, actually, and several more in the same set. We varied well, actually we varied the copper in this particular case, so we're basically going from excess copper to a deficit of copper. And we got this result. So this crossing point is clearly stoichiometry. This is where we want to grow, that's fine, but it's also kind of interesting in that we're getting, the arsenic is pretty much flat. It wants to be around about 33%, and it is around about 33%, so that makes lots of sense, even when there's large amounts of excess copper, which kind of implies that the copper is not forming copper arsenide, and actually we found out subsequently that it's forming just copper precipitates. It basically, the material just simply rejects the copper, it finds itself in a particular place and precipitates as little crystallites. Okay? The manganese doesn't behave like that. The manganese actually starts to take on more arsenic. So when you've got a manganese there, an excess of it, you actually get manganese arsenide, which we see in the squid. We clearly see a ferromagnetic signature. So it's clear that that's what we're growing. So basically, these are the problems that you have if you're off stoichiometry. But if you're on stoichiometry, you grow good quality material. It's also interesting for any growers around that the beam equivalent pressure is really weird. It's completely different from where we would have calculated it to be. Whatever. So, it's clearly not orthorhombic, so what is it? Well, normally what you'd do is you'd take the bulk that you think it is and kind of try and twist it and distort it to fit your X-ray peaks. That's what you'd normally do. And you'd find out a few peaks and try and work out the nature of that distortion, and the rest is easy to find. But it just didn't work. We couldn't make that work at all. So basically, my good friend Pete spent a long time really going through the literature and found some pretty obscure papers. This one's particularly obscure. I think was this in Russian, Pete? I think it was in Russian. Okay, so he found this Russian paper in Russian, and I think had it translated, and also this really nice paper by Pearson, which is in German. Now, Pete speaks German, so that's okay. That's not so bad. He was able to guess a model based on the sort of copper to antimony structure. The other good thing about the Pearson paper was that we proposed this structure up here, but the other good thing about it was that it gave us some rules, or at least it gave us potential rules for actually occupying the sites and saying which atom was going on which site. So not only did we have the structure, but we had some way of estimating the sites. We then simulated the diffraction pattern, as you might, and it fits absolutely beautifully. This is real data overlaid over the actual simulated pattern down here in this wide angle X-ray, and it's wonderful. Okay, so since we've got a model, we can now model what a TEM might look like, and it's very characteristic actually. You've got these copper planes here, and then you've got this sort of zigzag pattern with the arsenic. So if we have something that's Z resolved, if we can see the atomic number of the atoms, then we can actually see this pattern and confirm our structure. And this is beautiful work, again by Jaime Gasquez of Oak Ridge. He's kind of busy in this game. And you can probably see, maybe you can't, I don't know, but I'll show you other pictures anyway. There's sort of nice zigzag pattern going on here and the planes here. So it's pretty clear that we were on the right track, but just to confirm it, if you actually look at the integrated intensity along the rows, you've got this nice uniform amplitude here, and then you've got this varying amplitude or oscillating amplitude, bi-amplitude if you like, along the rows where you get manganese arsenic, manganese arsenic, manganese arsenic. So this actually pretty much put the nail in it for us. We were absolutely sure that we had the tetragonal structure, and that the atoms were in the place we thought they were. So this is great. Beautiful structure, overlays very nicely, looks very nice. So the question is the material defect-free? Nah. No, it's not. In fact, it's very difficult for it to be defect-free. You see, we're growing a tetragonal structure on a cubic substrate. So the step height of the cubic substrate and the step height of the tetragonal are not the same. They can't be. And inevitably, the material has to correct for that somehow, okay? Either by some distortion or some local strain at the interface, or by simply creating a defect. There's two ways it can do it. And certainly very much in the early structures, I don't know if you can see this, it's quite clear, there's the gallium arsenide there, and you've got the copper manganese arsenide here, and you've got a step height, and it just doesn't fit. So it goes, it just breaks, it just ships. These are actually called antiphase boundary. That antiphase, I had it pointed out by the previous speaker, actually, antiphase is a little bit of a misnomer, although that's the actual word that's used for these things. It's not really a different phase either side, actually. It's the same phase either side, it's just displaced by half of the unit cell. And you can see in this very early sample, it was one of the very early ones that we had done, a cluster of these things. So they exist and they branch and they do things, and they might even contribute to the strain relaxation of the material. But since this rather messy early structure, we've certainly improved the nucleation quite a lot, in fact a lot. The X-rays have improved, the full width half maxima have got less, and these things look a lot better, but I don't believe for 1 minute we've eliminated all the defects. We just haven't, okay? So does this matter? It depends. It depends what the defects do. Just as an aside, just to show you how defective a material can be without doing any damage. I guess 1 or 2 people in here might drive cars and drive down the road and look in their wing mirror or their center mirror, and they might see maybe an Audi or a BMW. Did you see that around here? Yeah, I see BMW cars. And you see the rows of lights, the frowny things that make it look like the car's quite angry, yeah? Those lights are gallium nitride. They're gallium nitride LEDs. And I used to grow gallium nitride back in the 90s. And when we were growing gallium nitride back in the 90s, the defect density of gallium nitride at that time was 10 to the 9 or 10 to the 10 per square centimeter. 10 to the 9, 10 to the 10, that's 1 billion or 10 billion defects per square centimeter. You wouldn't think you could do anything with that material. Nevertheless, you could grow LEDs. You could grow LEDs. And even now, the very best material they put in lasers is of the order of 10 to the 6, 10 to the 7. That's 1 million to 10 million defects per cubic centimeter. Yet, those lights in the Audi or the BMW or whatever car you've got, they have a mean time to failure of 50,000 hours. So these defects are not a problem in gallium nitride. So there are many, many material systems where having low defects doesn't matter. So if you see defects, don't go, oh my God, there's defects, it can't be used. That's not true. It's not true at all. So in this case, the question is, does it matter to us? And one way it might matter is it might basically donate electrons. But this is a semi-metal, so do we care? Nah, not really. If there's a few extra electrons, we're not bothered. It might, however, do something from the point of view nucleating domains. It might have an effect there. But what I can say, and I think we can say this with confidence, is the domains are much, much, much bigger than the separation of these things. So if it is having an effect on the domains, it's very subtle, because the domains span many hundreds, maybe even. So my answer to this is probably not, but it may have some subtle second-order effect. Okay, so this is it. This is the material. Basically grown using MBE on gallium arsenide, or actually now on gallium phosphide quite a lot. It's tetragonal copper to antimony structure. Relaxed mosaic blocks, you can see actually from the wide full width half maxima here and the quite broad spread in the reciprocal space. And you can also see that it's much more strained and coherent on gallium phosphide, much tighter, much smaller full width half maxima. And this is how we believe the structure grows. So it basically rotates by 45 degrees to the principal axes of the gallium arsenide. There's the gallium arsenide below. This is the copper manganese arsenide on top. It's rotated by 45 degrees and fits pretty well. The takeaway message from all of this, for anyone who wants to grow this stuff by sputtering or by MB or by whatever other method, is that the tetragonal phase is a metastable polytype. Okay? It's not the ground state of the system. Okay? And it's driven by the surface reconstruction of the substrate. And that's really rather important, and it's worth remembering if you're going to have a go at growing this stuff. It's not the ground state of the system. Okay? A little bit more, not much now, a couple of slides and I'm done, and then we can all have a cup of coffee. Thin films. We're growing quite thin films now. We can get down 10, even 5 nanometers. We've grown films with iron on top to look at things like exchange bias and other exchange interactions. It's quite versatile in that respect. The iron grows beautiful single crystal on top of the single crystal of the copper manganese arsenide. The X-rays from these thin films are fabulous. I mean, they're beautiful. They're really tight now with lots of fringes. So we're thinking that we're getting really quite good quality material here. And also, the anisotropy is very evident in these very thin films. And the anisotropy itself is probably driven by the interface. It's probably driven by the substrate interface. So the gallium arsenide is very important for the same reason that we get anisotropy in copper manganese arsenide, and for that matter in iron grown on gallium arsenide, we get anisotropy in this material potentially. And finally, some neutron diffraction data just to prove that it really is an antiferromagnet. Basically, this is the lovely Brouwer-like decay. This is the part of the signal that's only sensitive to magnetization, so of course it decays to 0, and here's a part which has some magnetic component and some structural component, and we can clearly say they decay at the same place, giving us a nail temperature of 485 Kelvin. With manganese moment, for what it's worth, of 3.6 Bohr magnetons, and this was measured at ICIS. They should change the name of that. At ICIS in the UK. Okay, so this is my conclusion. We have, I believe, grown copper manganese arsenide over a wide range of copper fluxes and seen the behavior, the fact this stuff really wants to grow. It rejects the excess material which grows precipitates, but basically between the precipitates and good quality material. We've shown it to be tetragonal, collinear antiferromagnet. That's the nail temperature. We've seen exchange bias with iron overlayer, other ferromagnetic signatures, neutron diffraction, etc. Now we've done electrical switching, which is nice. And I think there's got to be more, many more materials that could do the same job. We've just got to find them. And I mean, you could just go experimenting, sort of mixing stuff in a lab, or perhaps nowadays the more appropriate way of finding these things, now we know what to look for, is things like the work that Marcus and Jakob are doing, actually modeling these things and trying to sort of have high throughput models that get through materials. And if you feed the right information into these models, maybe they'll churn out structures that we could actually try to grow. And with that, I leave you with our paper, which we're quite proud of, and our little bit of switching there. And thank you very much indeed.